Thermo 2, Review of Thermo 1 Concepts. The basic idea of this review is to go over some of the thermochemistry concepts that we learned previously in the year and remind you of what you need to know. This will help you immensely as we go on and look at the second half of thermochemistry. So let's start out by looking at how to find the amount of heat released or absorbed per mole of substance. And the formula that we're going to use here is delta H over the moles of substance, where delta H is going to be in kilojoules and the moles of substance is going to be taken from a given balanced equation. So let's look at an example. How much heat, ultimately we're going to find that in kilojoules, is released when 2.5 grams of ammonium nitrate reacts. So here's our balanced equation right here. Ammonium nitrate decomposes into dinitrogen monoxide and water. And our delta H is negative 37 kilojoules. So the first thing that I'm going to do here is start out with my mass and convert to moles. Convert to moles, the AP chemistry mantra. 2.50 grams of NH4NO3, multiplication sign and a line. Whatever unit I start with is going to go on the bottom, so grams of ammonium nitrate all over 1 mole of ammonium nitrate, and the gram formula mass of ammonium nitrate is 80. So I'm going to do that, and then I know that grams will cancel grams, so I'm going to do 2.50 times 1 divided by 80, and I'm going to get 0.0313 moles of ammonium nitrate, NH4NO3. Once I have moles of ammonium nitrate, then what I can do is relate this number of moles of ammonium nitrate to my formula up here. So I'm going to just take this a step farther and put a multiplication sign and a line. And I know that looking at my balanced equation, that there is a coefficient of 1 right here. Coefficient of 1. So I know that for every 1 mole of ammonium nitrate consumed in this process, I'm going to release 37 kilojoules. And I know I'm going to release it because I see this negative sign right here. So 37.0 kilojoules. So that I'm going to put a negative there because I know it's going to be released. So as I work this out, again, moles cancels moles, I'm going to be left in kilojoules. So when I work this out, and I'm going to do this to 3 significant figures because I look back at my original problem, my given is to 3 significant figures. So this is going to be 1.16 kilojoules of energy. I can put a negative in front of it just to say that 1.16 kilojoules of energy is released out into the surroundings. Let's look at another example. The reaction for the combustion of acetylene is as follows. So I have 2 moles of C2H2 plus 5 moles of oxygen yields 4 moles of carbon dioxide and 2 moles of water. And overall, I'm going to have a delta H of negative 2,511 kilojoules. How much heat is evolved, which we know that's just another word for released, when 35.58 grams of C2H2 is burned in excess oxygen. And one thing that we can recall here is that since they're saying excess oxygen, we don't have to deal with a limiting reagent problem, which is awfully nice. So again, just like the previous problem, the first thing that I'm going to do is turn my mass into moles. So 35.58 grams of C2H2, multiplication sign and a line, 1 mole of ethine, or acetylene in this case, C2H2. And the gram formula mass of that is 26 grams of C2H2, because you should always label equals, and then I know that grams will cancel grams, so I'm going to do 35.58 times 1 divided by 26, and I'm going to get 1.368 moles of C2H2. 2. All right, so now I've converted to moles, which of course is the first thing that I want to do. The next thing I want to do is, again, relate this number of moles to my balanced equation and my overall delta H. So I have 1.368 moles of C2H2, multiplication sign and a line. And now here's the thing that you got to be careful about. This delta H is totally dependent on the number of moles of substance in your balanced equation. If I look at the coefficient in front of C2H2, I see that it's 2. That's basically telling me that for every 2 moles of acetylene is burned in excess oxygen, this is the overall amount of energy released. So I need to put a 2 on the bottom here, so 2 moles of C2H2 over negative 2,511 kilojoules. And again, like I've done before, moles cancel moles. And I do 1.368 times 2,511 divided by 2. And if I work that out, I'm going to get negative 1,720 kilojoules of energy released. So kilojoules, or you can put energy released. You need to show that energy is released as part of this process. And that's a little review of how to use that relationship between delta H and moles of a substance. Now let's go totally old school. How to calculate specific heat capacity of an object. Going back and revisiting our good friend Q equals MC delta T. Calculate the specific heat for water if 50 grams of water takes 209 joules to increase the temperature of water by 1 Kelvin. So nice simple question for us here. So we're going to do Q equals MC delta T. Always good to write your formula out first. We have 209 joules, which is going to represent our Q. Our mass here is 50.0 grams of water, so 50.0 grams of water. We are solving for specific heat capacity, which really you should know ahead of time, but hey, why not? And then our delta T, they're just telling us that our temperature is changing 1 Kelvin. So a difference here based on what you might have seen previously is this question is not giving you a temperature initial and a temperature final to find your delta T. They're just telling you the temperature change. So if we work this out, we find that the specific heat capacity of water is what you've already expected to be, 4.18 joules per gram Kelvin for our answer. So a little review of specific heat capacity. How to calculate the heat capacity of an object. So this is going to be joules over change in temperature in either Kelvin or degrees Celsius. If the temperature of a 150.0 gram sample of copper increased by 23.7 Kelvin when heated by 700 joules, calculate the heat capacity of the block. So in this case, I'm dealing with Kelvin, so I'm going to be using joules over temperature change in Kelvin. So I'm just going to plug my numbers in here. So I'm going to have 700 joules up on top, and we are just given a delta T. So that is 23.7 Kelvin. And if I work this out, and I should be doing this to 3 significant figures, I am going to get 29.5 joules Kelvin. 2 things to note here. This whole process is not mass dependent. It is not mass dependent, and the mass here is used as a distractor. So when calculating heat capacity, big thing to remember, not mass dependent, and the mass is included just as a distractor, so we're not going to be using it to calculate the heat capacity. If 50 milliliters of 0.1 molar AgNO3 and 50 milliliters of 0.1 molar HCl are mixed, the temperature increases from 22.3 degrees Celsius to 23.11 degrees Celsius. Calculate the delta H for the reaction given a total mass of 100 grams and the specific heat of 4.18 joules per gram Kelvin. The first thing that we want to do here is write the balanced equation. So my first reactant is AgNO3, and my second reactant is HCl. One of my products here is going to be the insoluble AgCl, and then my other product is going to be HNO3. And I know some of you might look at that and say to yourself, well, that's nitric acid, that's going to be fully ionized. But right now I'm just working on a very simple double replacement reaction and looking this over and making sure that it is all balanced, which it is. So I can at least look at the mole ratio between the reactants and the products, and I can see that this is balanced. The next thing that I want to do is solve for joules. So I'm going to use the formula Q equals MC delta T, and I'm going to use the information that they give me. And they tell me that my total mass here is 100 grams because I can look at the assumption that I have 50 milliliters here, I have 50 milliliters here for a total of 100 milliliters. And since this is primarily an aqueous solution, I know that 100 milliliters is basically going to equal 100 grams. So my mass here is going to equal 100 grams. Since the majority of my solution is water, I'm going to use the specific heat capacity of water, which is given to me, which is 4.18 joules per gram Kelvin. And then finally, I'm going to do change in temperature. And remember, when you do change in temperature is always going to equal temperature final minus temperature initial. So the final temperature that they give us here is 23.11. So 23.11 degrees Celsius minus my initial temperature, which is 22.30. So 22.30. If I take the difference of those two numbers, I'm going to get 0.81 degrees Celsius, which I know is the same thing as 0.81 Kelvin. So I'm going to just put that in here as 0.81 Kelvin. And then I'm going to solve for Q. So if I multiply together 100 times 4.18 times 0.81, I get roughly 339 joules. Or if I convert that over, which I'm going to do right now, it's going to be 0.339 kilojoules. And I want to convert it into kilojoules because later on I'm going to solve for delta H, and I'm going to need that in kilojoules. Now let's go on and find the number of moles of AgNO3 and HCl based on the information provided. To find moles here, I'm going to need to use the molarity formula. So molarity is equal to moles over liters. So let's start out with AgNO3. So I have 0.1 molar AgNO3. I'm solving for number of moles, and then I go back up to the top and I see that I have 50 milliliters, but I know that when I do the molarity formula I need to convert into liters, so this is going to be 0.05 liters, and I'm going to cross multiply and solve for moles. So if I do that, I find that I have 0.005 moles of AgNO3. Now I'm going to do the exact same thing for HCl, but I can basically look at the numbers here and say, oh, 50 milliliters and 0.1 molar HCl. So I'm going to have the exact same setup. So you could either just write that out and state the obvious, like, well, the numbers are the same, therefore my number of moles are going to be the same. Or you can do all the work like I am doing and do the calculations. So 0.05 liters, we're going to cross multiply again. And again, we're going to get the same number. So 0.005 moles of HCl, and that is based on the information that was given to us at the beginning of the problem. The final thing that we need to do here is find delta H, and remember that delta H will be given to us in kilojoules per mole, which is why on the previous slide we had to convert to kilojoules. So what we're going to do is going to take that 0.339 kilojoules and divide by the number of moles, and it doesn't really matter which one that we pick here because they are the same number of moles, 0.005 moles. And if we work that out, and we're going to go to three significant figures here, we will get 67.8 kilojoules per mole, and that's helping us find the delta H of our substance. So this is the enthalpy change per mole of AgNO3 or HCl. That's what this number is giving us right here. How to calculate an unknown when two objects are placed in the same system. Assume that no energy has been lost to the surroundings. So what we can look at here is basically the relationship between the energy lost plus the energy gained will equal 0, because we're saying that this is a perfect situation where no energy is being lost. Let's look at an example. A small coffee cup calorimeter contains 110 grams of water at 22 degrees Celsius. A 100 gram sample of lead is heated to 90 degrees Celsius and then placed in the water. The contents of the calorimeter come to a temperature of 23.9 degrees Celsius. What is the specific heat of lead? To calculate this, we're going to use the formula Q equals MC delta T, where one Q is going to represent our water and the other Q is going to represent our lead. So the way that we're going to set this up is we're going to say MC delta T is equal to negative MC delta T, because that whole relationship here basically is equal to Q is equal to negative Q, which we see up here. So the energy lost is equal to the energy gained. So what we need to do here is look at one side. We'll say this is going to be our water side. All the information being represented over here for water, and then all the information for lead being represented on this side. So we keep our information separate. So let's look at our problem again. A small coffee cup calorimeter contains 110 grams of water. So that means the mass right here is going to equal 110 grams. We know the specific heat of water is 4.18 joules per gram degrees Celsius in this situation. And then we have a change in temperature. And again, with our change in temperature, it's always going to be temperature final minus temperature initial. Now our final temperature here is where it says the contents of the calorimeter come to a temperature of 23.9 degrees Celsius. So that's going to be our temperature final for both of these situations. So temperature final will be 23.9 degrees Celsius. My temperature initial for water is 22 degrees Celsius. So 22 degrees Celsius. So if I take the difference of those two, my delta T for this situation is going to be 1.9 degrees Celsius. Okay, that is going to be my delta T. Now let's go over to the lead side. So we're going to have a negative here, and we've got to be really careful to make sure that we bring that negative with us. So I'm going to put brackets around here just to make sure that negative is really obvious. The mass of the lead. 100 gram sample of lead. So the mass of my lead is going to be 100 grams. We're solving for the specific heat of lead, so I'm going to have that represented by a C. And again, we have a change in temperature. So my temperature final will be the same thing as it is for the water, 23.9 degrees Celsius. And then my initial temperature of the lead is stated right here. Sample of lead is heated to 90 degrees Celsius. So my initial temperature of the lead is 90 degrees Celsius. Okay, so what I want to do here is I want to solve for the specific heat capacity. And if I do this, making sure that I watch my negative here and I distribute my negative all the way through, when you work this problem and you solve for the specific heat of lead, you should find it to be 0.132 joules per gram degrees Celsius. So you should work this through on your calculator and make sure that you got the same answer as I did. And this is an important concept to know to see how heat energy is transferred and also how heat energy is conserved when you're in a situation like a coffee cup calorimeter. Let's look at another example. A 45 gram block of a metal at 99.5 degrees Celsius is dropped into a 150 gram sample of water at 24 degrees Celsius. The temperature of the water rises to 26.4 degrees Celsius. The specific heat of the water is 4.18 joules per gram Kelvin. how much energy is gained by the water? Well, let's figure this out. And to do this, we're going to use Q equals mc delta T. The mass of our water here is given at 150 grams of water. We know the specific heat of water is 4.18 joules per gram Kelvin. And then we have our temperature change. So again, delta T will always be represented as temperature final minus temperature initial. And our final temperature here is 26.4 degrees Celsius. 26.4 degrees Celsius minus our initial temperature of water, which is 24 degrees Celsius. So 24 degrees Celsius. So when we work this problem, we're going to take the difference of our temperature change and we're going to multiply that times 4.18 times 150 grams. And if we do that, we should find that our answer is around 1,505 joules. 1,505 joules. And that is the amount of heat gained by the water. Now, how much heat is lost by the block of metal? Well, we know that the energy lost, Q, representing energy, plus the energy gained will equal 0. So if I look up at my previous problem and I see that the amount of energy gained by the water is 1,505 joules, that means the amount of energy lost must be 1,505 joules lost. Finally, what is the specific heat of the metal? All right, Q equals mc delta T. We know that the amount of energy lost by the metal is, we're going to put a negative to represent the amount of energy lost. So negative 1,505 joules is equal to the mass of the metal, which is 45 grams. So 45 grams. We're looking for specific heat here. The final temperature of our water metal mixture is 26.4 degrees Celsius minus the initial temperature of the metal, which is 99.50 degrees Celsius. And I put this negative here on purpose because when I take the difference in these two numbers, I'm going to get a negative number, and specific heat needs to be a positive value. So when I work this out and I solve for specific heat, I find that the specific heat of my metal here is 0.457 joules per gram Kelvin. And that is the specific heat of my metal. One more example. 25 milliliters of a 0.2 molar AgNO3 is added to 35 milliliters of 0.2 molar NaCl. AgCl precipitates and the temperature of the mixture rises 1.3 degrees Celsius. The heat capacity of the solution is 4.2 joules per gram Kelvin and the density of the solution is 1 gram per 1 milliliter. Let's start out by writing our balanced equation. Our first reactant is AgNO3, so I'm going to list that first. AgNO3. And we say that that is added to NaCl. NaCl, we're going to do a double replacement reaction here, and this reaction is driven forward by the formation of our solid AgCl plus NaNO3, which we know is very, very soluble. So if we were to do the net ionic equation here with no spectators, we know that the sodium is going to be a spectator, and we also know that the nitrate polyatomic is also a very soluble polyatomic. So when we rewrite this, because this is already balanced, we're going to have Ag plus 1 plus Cl minus 1 gives me AgCl solid. Determine the maximum amount of silver chloride formed. That sounds like a limiting reagent problem to me, and a good time to revisit how to do this. So remember, when we're doing a limiting reagent problem, we need a balanced equation like we have up here, and we need to solve for moles. So we're going to use molarity is equal to moles over liters, and I'm going to start out with the AgNO3 first. So 0.2 molar AgNO3. I'm going to solve for moles of that. And I'm in 25 milliliters of solution. So I'm going to convert that into liters. That's going to be 0.025 liters. And if I work that out, I am going to find that this is 0.005 moles of AgNO3. And I'm going to do the exact same thing now for my sodium chloride. So I have a 0.2 molar NaCl, 0.2 molar NaCl. I'm going to solve for moles on this one, but in this case I have 35 milliliters, so this is going to be 0.035 liters. And when I solve for moles here, I'm going to have 0.007 moles of NaCl. Now to figure out which one is my limiting reagent, I am going to go up to my balanced equation, which I have right here, and I'm going to look at the coefficients. And this is very, very easy because it's already balanced. Everything's in a 1 to 1 to 1 to 1 ratio. So I'm going to divide this by the coefficient in front of AgNO3, which is 1. Divide this by the coefficient that is in front of NaCl, which is also 1. And this is going to be 0.005. This is going to be 0.007, and I know the number that is smaller is going to be my limiting reagent, so that means my AgNO3 here is going to be my limiting reagent. Once I have my limiting reagent, I can figure out the maximum amount of silver chloride formed. Always go back to your original amount of moles of substance to start with. So 0.005 moles of AgNO3. Multiplication sign and a line. I'm starting with moles of AgNO3, so that is going to go on the bottom. I want moles of silver chloride, so AgCl, and I know that my coefficients here, because this is already balanced, is going to be 1 here and 1 here. And if I work this out with moles of AgNO3, canceling moles of AgNO3 and multiplying through, I'm going to have 0.005 moles of AgCl. And I didn't specify here if I wanted to go to moles or grams. So we're just going to leave this as moles right now, but this is also a little review of how to do a limiting reagent problem. So to summarize, I found my number of moles based on the molarity equation for each one of these. I looked at my balance equation, I looked at the coefficient, I divided each of my moles by the coefficient. The smaller number will indicate which one is my limiting reagent, and then in this case I just did a mole to mole problem, but if I had to take it a step further and find mass, I totally could. Now what I want to do is determine the mass of the total solution based on the information provided. If I look back at my original problem, I have 25 milliliters of AgNO3, and I also have 35 milliliters of my NaCl. So if I add those two volumes together, I will get a total volume of 60 milliliters. Now each of these is 0.2 molar, which means that both of these volumes that are listed right here are primarily water. Now in this problem, if you go back to the original, they tell us that the density of the solution is 1 gram per milliliter. So if I have 60 milliliters, I can figure out the mass here. So 60 milliliters of solution, and then I use the density right here, which basically says, well, 1 milliliter, because there's an assumed 1 down here, is equal to 1 gram. So milliliters cancels milliliters. 60 times 1 gives me 60 grams of solution. 60 grams of solution. Then calculate the number of joules formed from this reaction. So if I'm looking for joules, I'm going to use Q equals MC delta T. We just found that our mass of our solution is 60 grams. So 60 grams. They tell me back in the original problem that the heat capacity of the solution is 4.20 joules per gram Kelvin. And then finally, for my delta T, again going back to my original problem, they say that the temperature of the mixture rises 1.3 degrees Celsius, which is the same as 1.3 Kelvin. So they just give me my delta T here. They don't give me a temperature initial and temperature final. They just tell me the temperature change of the solution. So my delta T is going to be 1.3 Kelvin. Therefore, 60 times 4.2 times 1.3 will give me 327.6 roughly joules of energy formed from this reaction. And that's a little overview of a lot of the thermochemistry that we did at the beginning of the year.